Hello and welcome to Compassion. In this video, I will be explaining you about IR spectroscopy, basic principle of IR spectroscopy, what happens when uh, an organic molecule absorbs IR radiation, then what are the different fundamental modes of vibrations in IR spectroscopy, what is combination frequency, and Fermi resonance. So IR spectroscopy, as I explained in previous video, that it observes vibration of bonds and provides evidence of functional groups present in the molecule. In case of IR spectroscopy, it is actually non-destructive technique where the sample is not destroyed. What is the IR range? So generally the IR range is from 0.8 micrometer to 200 micrometer. So it involves far IR, mid IR and IR radiation. The most important range is mid IR range, which is from 2.5 micrometer to 15 micrometer. This is in terms of wavelength. In terms of wave number, it is 4000 centimeter inverse to 6600 centimeter inverse. So generally when we solve IR spectra, we get this in terms of wave number only, which is from 4000 to 600 centimeter inverse. The range from 4000 to 1500 centimeter inverse is called functional group region, and 1500 to 600 centimeter inverse is called fingerprint region. So what is the basic principle of IR spectroscopy? IR spectroscopy involves vibrational absorption. That is, when a molecule absorbs IR radiation, then it results in vibration of covalent bonds. And these vibrational motions are quantized. So how does this vibration or vibrational excitation occurs? This results in stretching and bending of bonds. So when the bonds are stretched and compressed, then in that case there is vibration of covalent bonds, and that is called as vibrational excitation. The basic selection rule for IR spectroscopy is that vibration must change the dipole moment of the molecule. That means there should be some change in the dipole moment of the molecule. If the dipole moment is equal to 0, then it is said to be, or that molecule is said to be IR inactive. But if the dipole moment is not equal to 0, which happens only when there is change in the dipole moment of the molecule, then the molecule is said to be IR active. So mostly if we have a symmetrical molecule, then the dipole moment is generally 0. For example, if I have carbon tetrachloride, so carbon tetrachloride is a symmetrical molecule. Here the dipole moment is equal to 0. So this molecule is actually IR inactive. But instead of taking carbon tetrachloride, if I take chloroform, then there is unsymmetry in the molecule, and in that case dipole moment is not equal to 0. So this is IR active. So I hope you understood. IR inactive molecule when the bonds are symmetrical and the dipole moment is 0. And uh, another example is of acetylene. Acetylene is CH, triple bond CH. So here also dipole moment is 0. So this is also IR inactive. But if I introduce one methyl group in this molecule, then this is unsymmetrical molecule. In this case, there will be some dipole moment, or there is a change in the dipole moment. So this will become IR active. So I hope you understood what are IR active molecules and which are IR inactive molecules. Now, what happens when a molecule absorbs IR radiation? So here we can consider covalent bond between two atoms as a spring. So when we stretch a bond, there will be some restoring pull towards the two atoms, which will bring those atoms to their equilibrium bond length. In the same manner, if the bond is compressed, then the restoring force pushes the two atoms apart. So when the bonds are stretched or compressed, then it will lead to vibration in the molecule. So here you can see that if I consider covalent bond as a spring, so when they are stretched, then there will be some restoring force which will pull the atoms together at equilibrium bond length. In the same manner, if we compress this covalent bond, then again there will be restoring force which pushes the two atoms apart, and this stretching and compressing will lead to vibration. So IR spectroscopy, if you want to calculate what will be, how much will be the vibrational excitation, what is the frequency, so that is done with the help of Hooke's law. Uh, so according to this law, we can say that the stretching vibration depends on the masses and stiffness of the bond. So if we have some heavier atom, they will vibrate more slowly than lighter ones. Obviously, if something is heavy, then it moves slowly. So here also, if the atoms uh, are heavy, then the vibration will be slower. If the atoms are lighter, then the vibration will be faster. So if I compare between carbon and deuterium bond, so deuterium being heavy, its frequency will be lower, or it will vibrate at a lower frequency as compared with carbon and hydrogen, because hydrogen atom is lighter than deuterium. So in a group, if we have some group of bonds with similar bond energies, then the frequency decreases with the increasing atomic weight. For example, if I consider bond between carbon hydrogen, carbon deuterium, carbon carbon bond, so as we move from carbon to hydrogen to deuterium to carbon atom, then the atoms are becoming heavier. Okay, so carbon atom is heavier than deuterium and hydrogen. So as the atom becomes heavier, or there is increasing atomic weight, then you can see the frequency of vibration decreases. So for carbon carbon bond, the frequency of vibration is 1200 centimeter inverse. For carbon deuterium, it is 2100 centimeter inverse, and for carbon hydrogen, it is 3000 centimeter inverse. So frequency decreases with increasing atomic weight. As the atom becomes heavier, frequency decreases. Second factor, as I said, that is stiffness of the bond. How strong are the bonds? So when the bonds are stronger, then they are generally stiffer. So in that case, they will be requiring more force for stretching and compression. And stronger bonds hence usually vibrate faster as compared with weaker bonds, if we consider atoms having similar masses. So if we compare between OH bond and carbon hydrogen bond, so OH oxygen hydrogen bond is stronger as compared to carbon hydrogen bond. So this OH bond will vibrate at a higher frequency, that means it requires higher energy for vibration. Similarly, triple bonds are stronger than double bonds. So triple bond will vibrate at higher frequency as compared to double bonds, and double bonds vibrate at higher frequency than single bonds. So in a group of bonds having atoms of similar masses, the frequency increases with bond energy. So here if we have bond between two carbon carbon atom, that means their masses are same. But we have carbon carbon single bond, double bond and triple bond. And as we know that triple bonds are stronger than double bond, and double bond are stronger than single bond. So stronger bonds will vibrate at a higher frequency. So frequency of vibration for carbon-carbon triple bond is 2200 centimeter inverse as compared with carbon-carbon single bond whose frequency of vibration is 1200 centimeter inverse. So in all we can say, or we can summarize this as that frequency of vibration is directly proportional to strength of the bond. Stronger the bond, higher will be the frequency of vibration, and it is inversely proportional to masses of atoms bonded to one another. That means heavier the atom, lesser will be the frequency of vibration. Now let's see what are the fundamental modes of vibration. That means when a molecule absorbs higher radiation, there are stretching and bending of bonds. So these stretching and bending vibrations are again divided into different classes or categories. So stretching vibrations can be of two kinds. Symmetrical stretching, where you can see if we consider these three atoms, so both this blue and red, they are pulled outside and then pushed inside. So both outside atoms, they move away or toward the center. So this is called as symmetric stretching vibration. Second is asymmetric stretching vibration, where one atom moves towards the center and the other atom moves away from the center. So then it is called as asymmetric stretching vibrations. Bending vibrations are of four kinds. First is symmetric bending vibration, which is in plane. So here both the atoms, this symmetric bending vibration is called as scissoring vibration. So it moves like a scissor. So both the atoms, outside atoms, they will move inside and outside, and both of them remain in plane. So this is scissoring. Similarly, we can have asymmetric bending vibration. This is also in plane, which is called as rocking. So one atom moves in this direction and the other moves in this direction. And then this will move in counterclockwise manner, and this will go in clockwise manner. So this is called as rocking vibration. Both scissoring and rocking bending vibrations are in plane vibrations, where all atoms are in the plane. Next type of bending vibration is out of plane bending vibration. In short, we write it as OOP, where it is called as out of plane. So in this, again, we have symmetric bending vibration, which is commonly called as twisting vibration, where if you are watching this video on your phone, so this one atom will go below the plane of your mobile phone and the other will come above, and then they will just twist. So that is twisting vibration. And then we have asymmetric bending vibration, which is again out of plane, commonly called as wagging vibration, where both of these will come forward and then they'll go behind. So that is called as wagging vibration. So these are the fundamental modes of vibration. Stretching are of two types, symmetric and asymmetric, and bending vibrations are of four types, two in plane, scissoring and rocking, and two out of plane, twisting and wagging. Now, how do we find out that a particular molecule will show how many modes of vibration? So, first of all, it depends upon whether your molecule is linear or non-linear molecule, and depending upon that, we have the formula to calculate total number of fundamental vibrations. So, if the molecule is non-linear, then it is 3n minus 6. We can use this to calculate total fundamental modes, vibrational modes of vibrations, where n is the number of atoms. For example, if I take water, so water contains three atoms, two hydrogen and one oxygen. So total modes of vibration is 3. So we know that water molecule is actually angular in shape, so that is a non-linear molecule. If we have linear molecule, for example, carbon dioxide or acetylene, then in that case we use the formula 3n minus 5, where again n is number of atoms present in the molecule. So here I have shown the three, because for water there are three modes of vibration. So I have shown all three modes of vibration. There is symmetric stretching, anti or asymmetric stretching, and scissoring vibrations. So why does these fundamental vibration occur? So this is due to excitation from ground state to lowest energy excited state in vibrational energy level. So it is not in electronic energy level, but it is in vibrational energy level. We can say there is excitation from ground state vibrational energy level to first excited state vibrational energy level. To understanding what are fundamental modes of vibration, the next term which is very important is overtones. So what are these overtones? So when a vibrational excitation occurs when a molecule absorbs IR radiation, so that excitation is from ground state to excited state. But if this vibrational excitation occurs from ground state to second or third or even fourth excited state, then they are called as overtones. So generally these vibrations are weak vibrations. So as I told you that fundamental vibrations are vibration from lower vibrational energy level to higher vibrational energy level, that is mu naught to mu 1. But if it goes from ground state to second or third or even fourth excited state, then they are called as overtones. So generally overtones are integral multiples of fundamental vibrations. So whatever fundamental vibration you have, if you want to find out overtone, it will be 2 into mu or 3 mu or 4 mu and so on, depending upon in which excited state it is going. So if you have absorption fundamental vibration at 600 centimeter inverse, so it may show weaker overtones. So that will be 2 into 600, that is 1200 centimeter inverse if it is going from mu naught to mu 2. Similarly, if it is entering into third excited state, then it will be 3 into 600, that is 1800 and so on. So this is how we calculate overtones. What are combination frequencies? So when two vibrational frequency, that is mu1 and mu2, in a molecule coupled together to give rise to a new vibrational frequency which is actually IR active, then it is called as combination frequency. So simplest formula for combination frequency is mu1 plus mu2. So you get another frequency which is IR active, so that is combination frequency. Similarly, we can have difference band where we take difference of the two vibrational frequencies. Fermi resonance or coupled vibrations. So sometimes it happens that you have some overtone or combination frequency which is lying near a strong fundamental vibration. So in that case, what will happen? Both of them, that is these overtones and strong fundamental vibrations, they will couple, and that results in change in the intensity. Such interactions are called as Fermi resonance or coupled vibrations. As I explained earlier, that mid-IR region is actually needed for an organic molecule for stretching and bending vibrations. So, and I also told you that the if you see IR spectra, actual IR spectra, so left hand two-third of IR spectrum, which ranges from 4000 to 1500 centimeter inverse, is where most of the functional group will show absorption bands. So that region from 4000 to 1500 centimeter inverse is called as functional group region because most of the functional groups can be identified in that particular region. And the region 1500 to 600 centimeter inverse is called as fingerprint region. Why do we call it as fingerprint region? Because no two people can have same or identical fingerprints in the same manner. In this particular range, no two molecule can have similar kind of vibrations because this range shows very complex vibrations. So if you have similar kind of vibration, that means it is one and the same molecule. That is the reason we call it as fingerprint region. So it is highly unlikely that IR spectra of two different compounds will show same frequency for all their various complex vibrations. And that is the reason it is fingerprint region. So as I said that 2/3 of left hand side of the spectra, so here from 4000 to 1500, so this range is actually functional group region where you can identify most of the functional group present in the molecule. And 1500 to 600 centimeter inverse, which is actually a very complex range, is called as fingerprint region. I hope you are understanding this. So if I say IR absorption of different bonds, depending upon whether you have single bond, double bond, or triple bond in the molecule, or you have some atoms which are bonded to hydrogen, then we can have different region. For example, fingerprint region, generally it is utilized to find out carbon-carbon single bond, carbon oxygen, carbon nitrogen, or carbon halogen single bond, which is from 1500 to 600 or 400 centimeter inverse. Then comes double bond region, ranging from 2000 to 1500 centimeter inverse, which is helpful in finding out the presence of double bond in the molecule. Like if you have carbonyl group, that can very easily be detected uh, by finding the bands in this particular region. Then we have triple bond region ranging from 2500 to 2000 centimeter inverse, which is typically utilized to find out presence of carbon-carbon triple bond and carbon-nitrogen triple bond. And if you have bonds to hydrogen atoms which are bonded to hydrogen atoms, then that can very easily be identified by finding out bands in the range of 4000 to 2500 centimeter inverse. So I hope you like this video. In coming videos, I will be explaining you uh, like which particular functional group gives vibration at what particular frequencies. So thank you for watching. Please like, share and subscribe.